they first start recording this velocity at t equal 21 seconds. Let's see. Oh, there we go. So at t equal 21 seconds, they recorded a speed. It was 697 kilometers per hour. Of course, we need to convert that into meters per second. You will have to do that for the test. Let's just do it just to remind you. So I know that in 1 kilometer, kilo means 10 to the third. There are 1,000 meters. My kilometers cancel and leave me with meters. That's how I know what goes where. And then in 1 hour, I put that in the numerator so that that cancels. 1 hour, let's see, 60 seconds in a minute, 60 minutes in an hour, 60 times 60, that's 3,600. So in 1 hour, there are 3,600 seconds, and then that's equal to 194 meters per second. And then don't forget, too, that if you have a unit that is squared or cubed or whatever, then you will square or cube the conversion factor. You'll probably have to do that on the test. So that's from chapter 1. Make sure that you're up on that if you're not just yet. So that was his speed at t equal 21 seconds. I want to calculate what his actual velocity should be. So if I just consider the acceleration due to gravity, the acceleration due to gravity is minus 10 meters per second squared. And if I want to calculate that speed at t equal 21 seconds, I remember my two equations for kinematics that we derived. And remember, you need to know how to derive them. They start from these definitions: a equals dv dt, and then v is equal to dx dt. And then you can solve functions for v and for x. We went over that last time, but make sure that you're able to recreate that. I'm just looking for you to be able to spit it back up onto the page, okay? And I know that's just memorization, but there's some value in that as well. So anyway, we have these two kinematics equations. V equals v naught plus at. And then also y equals v naught t plus 1/2 at squared. Notice here I left off the initial position because why not? Because it's 0, right? So because y naught is almost always 0, because that's where we set our coordinate system to be, at y naught equals 0. So these are our two equations. I always like to just write them down so I have them in front of me as I'm going through the problems, and you'll have a couple of kinematics problems you'll need to have them for. If I want to know what is v, what should v be, I know v naught here is equal to 0, or at least I'll assume it to be 0, that he's at rest when he jumps out of the balloon. V then is equal to, well, let's see, let's look at these equations. What do I know and what do I not know? I'm going to put a red line under what I don't know. I don't know y. I don't know v and I don't know y. But it looks like I know everything else. If I want to know the final velocity, it's right here. So I just say it's v naught plus at. And that's 0 minus 10 times 21 meters per second. This is actually a plus negative 10 because that's my acceleration due to gravity. So that's minus 210 meters per second squared. Notice it comes out negative. That just means that we have a speed of 210 that's directed downward. I'm sorry, this shouldn't be squared. This will be just meters per second. I'll fix it when I go back. So this is just meters per second. Oh, gosh, I'm sorry. And this should be seconds. Yes, Asia? The acceleration, whenever we're dealing with free fall problems, the acceleration will always be negative 10. So when you see a problem, you want to ask yourself the question, is it horizontal? In which case the acceleration is not negative 10, it's whatever it is, you might have to find it. Is it vertical? The acceleration is always going to be negative 10, at least for this chapter. In chapter 4, we'll have some vertical motion where it's not that. But as far as we're concerned right now, in the y direction, this is always going to be our acceleration. Okay, so let me tidy this up, fix it a little bit. This should have been seconds, and this should have been meters per second. Remember, this was meters per second squared, so that cancels with seconds to give me meters per second. All right, so I have two values here, 194 and 210. They should be equal, but they're not. So with these assumptions that I've made, I get a speed that's a little bit higher, although remarkably close to what we have here. There are several reasons why this can be. Can y'all think of any reasons why this value is bigger than this value? A few things. Okay, yeah, the drag. There's not a whole lot of drag at such high altitudes because there's just not a lot of atmosphere. In fact, as you watch it, he sort of eventually he'll reach a maximum speed and it just plateau at that speed and then continue falling at that speed. That's when he reaches the point where the force of the drag of the air resistance is equal to the weight. We call that the terminal velocity. We're not going to talk about that in this class, but you might have heard that before. I think they made a movie. Did they make a movie, Terminal Velocity or something? Anyway, so it's not accounting for air resistance, which would lower this number a little bit. There's another thing. Y'all probably don't know this, but you will when we get to fields, gravitational fields. Do y'all know what happens to the gravitational acceleration as you go higher and higher? It decreases, right? So the further you go away from the Earth, the more your acceleration decreases. So the acceleration is probably not quite -10. It's probably a little bit lower than that. So there's a good couple of reasons. There could be another reason. Our assumption for the initial velocity here is likely wrong because that balloon isn't really stationary. It's actually in this sort of orbit. And in an orbit, something is constantly falling towards the Earth. Are you aware of that? Have you heard that before? That when I have something that's in orbit, say this is the Earth and this is a satellite, it's constantly falling towards the Earth, but it has enough horizontal velocity so it doesn't fall straight down, but it follows this trajectory. It's always falling towards the Earth. That's why the Vomit Comet astronauts practice in it. It's a plane that goes up and then it falls down, and that simulates weightlessness. Falling is weightlessness. You could go jump off this building, and for just, a second or so, you would be weightless. Hey, let's do that. That's one thing that every nickel student should do. Jump off the second floor of Beauregard. I'll call maintenance. They'll let us up there. Okay? All right. Let's do a supplemental problem. So, I really recommend that you go through the homework. You really should go through the homework because sometimes I'll just go through the homework and say, hey, that's a good problem. And I'll put it in the test or something very similar to it. That is something that I use for our test questions. But you also have these supplemental problems that they're a little bit more difficult. I thought we had worked through some of them in class. If you have to use the quadratic equation as you do in one of these, do you have to use the quadratic? Forget. Wait, no, you don't have to use the quadratic. But if you need the quadratic, I'll give it to you. So don't bother memorizing it. Probably not going to use the quadratic. All right, so let's look at this. A squirrel falls out of a tree. This is on page 64. It's right after the homework. A squirrel falls out of a tree that is 3 meters tall. So I have this squirrel. It falls a distance of 3 meters. And I want to know a couple things. First, I just want to know what is the squirrel's velocity just before hitting the ground. That one should be pretty straightforward. That's just like the Red Bull that we just did. Instead of Felix Baumgartner jumping from however many kilometers above the surface of the Earth, you have this squirrel that's jumping from 3 meters, from about 10 feet. And I want to know his velocity. I can write down a couple of things that I know. Gosh, what do I know here? I always like to start with this. What do I know in this problem? And there are one, two, three things, three pieces of information that I know. And you can look at it and you see one thing right here. Right, so that is my what? That 3 meters. What variable is that? Right, that is my y. Well, I want to be careful. Is that my y initial or is that my y final? Usually, you could say either, right? But I'm going to say that it is my y final. And that comes about when I set up my coordinate system. Let me show you. Because if I set up my coordinate system so that it starts right here, so that this is y equals 0, that's y naught, then this, y, would be equal to negative 3 meters. That's just sort of the way I do it. You could do it a different way, but I find that this is a little bit easier. So I let this be 0, the beginning point where he is, and then this is my final position. You can play around with that and practice what happens if you switch those up. The numbers just come out a little bit differently. So y then is equal to negative 3.0 meters. Be careful with your signs. Uh, if you put a positive here, likely what will happen is you'll find that you'll solve for a negative time, or you'll find that time is some square root of a negative number. And if that ever happens, you should go back and check the signs, especially for your y position and your initial velocity, or your velocity as you travel along. So here my y is negative 3. What else do I know? There are 2 other pieces of information. I know acceleration. That's negative 10. And then one thing that's not stated in the problem, but I know it to be true. Let's think about it. I have the squirrel. He's in a tree, and then he falls out of the tree. What do I know about that squirrel? I know his initial velocity. I know that his initial velocity is equal to 0. All right. I'm looking for the squirrel's velocity. So this is just like the Red Bull problem. V equals V naught plus AT. Oh, but goodness, I can't solve this because I don't know the time, right? So the first thing that I need to do is to find the time. I'm going to write down both equations. Y equals V naught T plus 1/2 AT squared. I'm going to look at these equations and ask myself the question, what are the unknowns? All right, well, V is an unknown and T is an unknown. Those other things are known. So it looks like I just have T here and T here. You agree those are my only unknowns in these equations? Listen, these kinematics questions, once you get past this point, largely they become exercises in algebra. And so you'll need to be sort of up on your algebra. And we'll in fact do some substitution problems where we're substituting one equation into another. Probably going to see some sort of substitution, like we'll do the next one, which is like that. So what I want to do first, 2-step problem, solve for time. Using this equation, I say negative 3 equals 0 times t plus 1/2 negative 10 times t squared. This term goes away. I get negative 3 divided by negative 5. Square root of that is going to equal to t. And that's going to be 0.77 seconds. Again, if you chose, or if you assign this as a positive value, then you would have a positive value here, and then you would have the square root of negative 3 over 5, which is an imaginary number. It would be like 0.77i. And we're not dealing with imaginary numbers, so if you get the square root of a negative number, you want to say, I need to go back and check what I've done, that I have some problem in my algebra, and where I've assigned signs. Okay, so now I solve for t, and now that I know t, I can take this and find his velocity. So I say v is v naught plus at, 0 minus 10, that's my acceleration, times 0.77, that's 7.7 seconds. Or excuse me, 7.7 meters per second. All right, so that's part A. Part B says that this squirrel, when he lands, sort of looks like a spider, but when he lands, his legs he first has out like this, and then he lets them bend, and so it absorbs some of the shock. That's how animals are able to do that. That when they land at a pretty high speed, 7.7 meters per second, almost 10 meters every second. You just went 10 meters. This is pretty fast, 7.7 meters per second. And so when he lands, he bends his limbs, and that causes him to decelerate before he actually hits the ground. So he absorbs that impact into his limbs. And it says that it stops over a distance of 2 centimeters. So this is my distance, y equal negative 2 centimeters, which is negative 0.02 meters. You follow what I'm saying here? Over this tiny little distance at the very end of his fall, he falls 2 centimeters, but decelerating at a rate so that when he reaches the ground, he's at 0 speed. So what do I know? I know that y naught equals 0, y equals negative 0.02 meters. What else do I know? This is a little trickier. Do I know my acceleration? I don't, in fact. Well, just a second, Catherine. I don't know the acceleration because this squirrel has been falling at an acceleration of negative 10, but when he puts out his legs, he slows himself. So now he's actually decelerating at some rate that I'm not sure what it is. So he's decelerating at this point. So I don't know what the acceleration is. Catherine? Yes, you're right. It should be negative. Thank you, Catherine. All right. So I don't know the acceleration here. Do I know his V naught? Or do I know his V final? What is his initial velocity? And it's like we have a different little problem. The, the initial condition of this problem is right as he puts his legs out. And then the final condition is when he's all the way down to the ground. So what is my initial velocity? It's negative 7.7. He falls, he puts his legs out, and at that point he's going negative 7.7 meters per second. And his final velocity then is going to be 0 meters per second. All right. Um, I don't know the acceleration. I also don't know the time. The question is actually asking what is the deceleration. Uh, and in order to do that, I'm going to also need to find the time. Let's just sort of take a quick little check. Is this acceleration, is it going to be positive or negative? Remember, if velocity and speed are in the same direction, you're speeding up. If velocity and speed are in opposite directions, you're slowing down. What's this guy doing now? Is he slowing down or speeding up? He's slowing down. And the direction of his velocity is negative or positive? It's negative. So the direction of the acceleration then, if he's slowing down, must be positive. So when we find this acceleration, we're going to find that it's going to be positive. Okay, so V is negative 7.7, or 0, V naught is negative 7.7. Let's write our equations. I have V equals V naught plus AT, Y equals V naught T plus 1/2 AT squared. All right, now this is where it gets a little tricky. You want to be a little bit savvy with your algebra because in both of these equations I have two unknowns. See, I don't know A and I don't know T in both of these. So what you want to do is to solve one equation and then substitute it into the other equation. You've solved systems of equations before. I know that you have. It might have been a while, but you need to get practice on this right now. Your algebra needs to be a little bit not rusty. So you want to look at this. There is an easy way to do this so that you don't have to use the quadratic formula. And the easy way to do this is to solve this for A, and then you're going to plug that in here. And let me show you why. Because if I solve that for A is V minus V naught over T, and then I take this and I plug it in here, Notice that I have a t squared in the numerator and a t in the denominator. It'll cancel out one of those. It'll make solving it a lot easier. You don't have to futz around with the quadratic equation. But who likes to do that, right? No, not me. Not y'all either, probably. Okay, so I'm going to substitute that in. I'm going to say y equals v naught t plus 1 half. And now a becomes v minus v naught over t times t squared. I can cancel a couple of things, get rid of that and that. In fact, I'm going to go ahead and get rid of this too because it's equal to 0. So now I get a fairly simple expression, v naught t minus v naught t over 2. And that is equal to 1 half v naught t. If I put in my value for v naught here, and I know my value for y here, then I can say y equals minus 1 half v naught t, solve for t, and I find that t is equal to 5.19 times 10 to the minus 3 seconds. And then, I really want to find the acceleration. And so I take this and I plug it in up here, and getting the acceleration equals 0 minus negative v naught, which is 7 point, or minus v naught, which is 7.7, divided by t, which is 5.19. That is equal to 1480. Okay. Solving, it's a good skill to solve equations by substitution. Just, need to take out your algebra and sort of shake it out, knock the rust off and get the dust off and make sure that you can do this. It's an important skill anyway for you guys because you're, engineering and chemistry majors, most of you geomatics, it's stuff that you need to know how to do. All right. Y'all good with me on this so far? Yeah. Are you right here? Or the first V naught? Oh, it should be 1 half V naught T. Where did that negative? Yeah, this is supposed to be a positive right here. Let's see. Where did that come from? Oh, wait, no, that's right. It should be positive. Let me step back. I don't think that answers your question. See, I have here V naught T, and right here I have 1 half V naught T. 1 V naught T minus a half V naught T, that's equal to positive a half V naught T. Right. And then down here, this should be positive. Since this is negative and this is negative, then our T comes out to be positive. There's going to be lots of signs floating around on your exam, and you need to be careful about following what's what. Fortunately, I don't count off a whole lot if you just get a sign wrong, but it can make it difficult to grade and difficult to sort of get to the right answer. I will do my best to try to follow what it is that you're doing. Just just a little hint to you that I know some of you are going to do really well on the exam and your handwriting's kind of messy. Uh, and that's fine. Like I'll grade it fairly, but sometimes if it's hard for me to see what you're doing, it's hard for me to give partial credit. So if you're a person that has bad handwriting, like me, did I tell you I made a D in handwriting in 4th grade? Lynette Harris gave that grade to me in 4th grade, a D. Anybody else? Bad handwriting? You too, Sadie. Jesse. Okay. Wanna? No. They made me wear this pencil. I had it like strapped onto my hand because I was left-handed, and they thought, I must be deformed or whatever. And so they put this pencil on my hand, and it's like trying to make me write the correct way. Anyway, the point is, use good handwriting. It will help me to grade your tests with greater grace. Okay? If you get something wrong. If you get it right, you're going to get it right, whether you've been handwriting or not. Okay, let's save these other two supplemental problems. We might have time at the end of class, but let's go back and look at some other problems that are a little simpler. Back in the notes. Now let's look at a couple of free fall problems. You'll likely have some free fall problems, and we'll see one in the supplemental problems. But let's work this free fall problem. First, I'm going to show you a little video. This is a video of Big Buck Bunny. Have you ever watched Big Buck Bunny? It's a little online movie. It's about this big, really naive bunny rabbit. He's about 6 foot tall, and he's kind of a big bunny. And he's being bullied by these three animals, a flying squirrel, and then a couple others. I don't know the word. The flying squirrel, he's like the lead bully. And in this final scene, Big Buck Bunny is exacting his revenge on the flying squirrel. So Big Buck Bunny, he looks like the bad guy. Well, I guess he probably is the bad guy, but he's really, well, he's getting revenge. Don't go out and get revenge. That's not good. But anyway, there are a couple of instances of free fall that I want you to notice. And as we watch it, notice what the instances of free fall are. And then from the video, think about what is some information that you can preen from it about that free fall. And in the course of that, we'll see two separate free fall problems that you work two different ways. All right. So when the peach fell, it falls in slow motion. So we can't get any time information about that. It's a problem where we don't know the time. So let's look at that. I have a peach that falls out of a tree. Falls out of a tree down to the ground. I want to know a couple things about it. I want to know what is the total time that it takes to fall, and then also what is the velocity that it falls when it reaches the bottom of the ground. Kind of like the Red Bull problem that we were looking at. I know a couple things about this. I know the acceleration is -10. That's because it's the acceleration due to gravity. It's falling vertically, so it's -10. It's in free fall. I also know that V naught is equal to 0. And then I can make some assumptions. I'm just going to assume what is this distance. Let's see, what did I assume? What do you guys think about how far is that roughly? A tree, a big tree, in feet. I mean, 20 feet? I said 60 feet. I guess my tree is bigger than your tree. I'm going to say 20 meters. All right. So my distance, y, is it equal to 20 meters? Should it be positive or negative? It is negative, right? And remember, that goes back to our coordinate system is right here. That this is y naught equal to 0. So this is y equal to -20. Okay, so now I want to know what is his final velocity. I know that v is equal to v naught plus at. I don't know v, and I don't know t. So in order to solve this, I need to find out what t is. Let's look at the other equation. Y equals v naught t plus 1/2 at squared. Let's see, this is 0. And I don't know t, but I know everything else. So I can solve this for t. It's very fortunate that v naught is equal to 0 here, because otherwise you'd have to use the quadratic. If you ever have this equation and v naught is not 0, you have to use the quadratic. So I get -20 equals 1/2 of -10, that's -5, times t squared. So t is the square root of 20 over 5, square root of 4, which is 2 seconds. So that's one part, is 2 seconds. And then I can take this and plug it in here. And I get this is 0 minus 10 times 2, which is 20 meters per second. That's the second part. That's a pretty simple kinematics problem. You could have one like that, but you'll also have one that's a little more complicated. Okay. Right, 20 divided by 5 is 4, but then the square root of it. The square root of 4 is 2. Oh no, this is my S. This is Chad's D handwriting S. Did I tell you I made a D in handwriting in 4th grade? I did tell you. Lynette Harris. How did you, Lynette Harris? No, she's still very important to me. I still talk to her. 4th grade teachers, man. I love those women and men. They're men too. But all right. Yeah, Catherine. Huh? Yes. So negative 20 right here. Alrighty. Now I also have a second instance when the squirrel fell. So the squirrel fell, and in this I know the time because it wasn't in slow motion, and so I just watched the clip and I picked off the time. So the time is given, and that time is t equal 4 seconds. Notice that the time here for the squirrel to fall is twice the time for the apple to, or the peach to fall. So I want you to think about before we go any farther, how is the distance and the speed going to compare? Now on this one, our distance was 20 meters. Now I have twice the time. Is it going to be 40 meters? Or is it going to be 60 meters? Or is it going to be 80 meters? From what distance does this squirrel fall? If it requires twice the amount of time, how does that affect the distance? And then the other thing is, the peach, when it fell, it was going 20 meters per second. What speed is it going to be going, the squirrel, having fell twice the amount of time? Is it going to be going 20 meters per second? Or 10 meters per second? Or 40 meters per second? Or what? We're getting to, is this a quadratic relationship? Or is it a linear relationship? Or is it something else? Okay? We could probably just say, well, I know the answer has to be this and this. Might not have that right off, but let's see what the answers are. So first, let's find the speed. V equals V naught plus AT. His initial velocity is equal to 0. His acceleration is equal to negative 10. And that's all I know. I know the time is 4 seconds. If you have the time in these problems, it makes them a lot easier. So if you come across a problem that has time in it, say, thank you, because it's going to be a lot easier with the time. I have 0 minus 10 times 4, negative 40 meters per second. So between the peach to the squirrel, by how much has my velocity increased in magnitude? It's doubled. I double the time, I double the speed. And that's because this relationship is a direct proportionality. If I increase if I increase t by a certain amount, I increase v by that same amount. It's a linear relationship. V and t are linear. Now also let's find out what is y. This goes away because v naught is equal to 0. I get negative 5. That's half of negative 10 times t squared, which is 4. That's 5 times 16, negative 80 meters. By what factor is this value greater than for the peach? 4 times as big. I increase the time by a factor of 2. I increase the displacement by a factor of 4. And that's because this relationship is quadratic. Y is proportional to t squared. So if I double t, I quadruple y. You'll see some questions like that. We had one in chapter 1. Remember I gave you that relationship and asked you how the variables changed? And we'll see that again on the test. Let's do a few clicker problems. Does anybody recall where we left off last time? Or do you have that written down, the number? Somebody does, I know you do. What's that? 2 point what? 2.3 is no. Do y'all recall, where do we leave off? 2.9. Oh yeah, this one. Okay, good. So we're thinking free fall in these. Bill and Alice are at the top of the building. Alice throws her ball downward, but Bill drops his ball. So Alice takes it, and she throws it down, and Bill just drops it. Uh, After they leave their hands, after release, which ball has the greater acceleration? Alice throws it, give it a certain initial velocity. Bill's initial velocity is 0. But after release, which has the greater acceleration? Alice's Bill's are, neither, or it depends how hard it was thrown. I'll stop at 58, 58. Okay, good. C is right. They're both going to have the same acceleration. They're in free fall. Alice's is going to be going faster, but they're both going to be accelerating at the same rate. Just because something's going faster doesn't mean that it's accelerating faster. It just means that it's traveling faster. Acceleration and velocity are different things. And when you're in free fall, you will always have the same acceleration. You throw a ball upward with an initial speed of 10 meters per second. What is its speed when it returns to you? So I throw something, ball, up, comes back down. What is its speed here? It's 10 here. What is it when it comes back? All right, I'll stop at 40. Pretty well. Remember, feel free to ask your neighbor. Okay, B is right. Remember, I gave you those properties of free fall. I want to go back and look at those. We'll work through some more free fall type problems later, but on Monday. But the speed here is going to be equal to the speed here. Whatever I throw it up at is the speed that it comes to back. So if I throw it up at 10 meters per second, it goes up, and then it comes back down with that same speed. Now it's a different velocity because it's going down instead of up, but they have the same speed when you come back to your hand. B is right. You drop a rock off a bridge. When it's fallen 4 meters, you drop a second rock. What happens to their velocities? I drop a rock. A few seconds later, I drop a second rock. What happens to their velocities? Stop at 45, 45. Okay, both will increase at the same rate. If you look at these other options, looks like B and D, the velocities don't stay constant because they're in free fall. The velocities are definitely going to change because they're in free fall and they're going to be accelerating at a rate of minus 10 meters per second squared. The velocity of the first rock increases faster than the velocity of the second. This sort of sounds right because, the first rock is traveling faster, but just because it's traveling faster doesn't mean it's accelerating faster. It's only traveling faster because it has that initial bump of speed. And so it's only traveling faster by that amount V naught. Where was it? Do we have a figure? I guess not, but she gives it an initial V naught by dropping it later. It's sort of like the Bill Alice problem. She drops it later. It has a little extra V naught, the first one that she drops, a little extra velocity. Right, so A is the right answer here. Both increase at the same rate. All right, this graph of a position versus time for a car is given below. What can you say about the velocity of the car over time? You will have some of these too. These will probably be multiple choice, or they might be part of a bigger problem where I ask you to draw the position of velocity versus time graph. So make sure you're up on these. Remember, the slope of a position versus time graph gives me the velocity. The slope of a position versus time graph gives the velocity. So what is this car? What can you say about the velocity of this car over time? Stop at 45, 45. Listen, y'all ask your neighbors. Y'all are sort of all over the board here. Y'all been all over the board all morning. Ask your neighbors, sort of see what they put. Uh, talk about it a little bit. I know it's Friday. I know y'all are tired because, what'd you call it? The Devil's Triangle? Is that what you called it? Definitely is. Funny article. Okay. We'll stop at 118. 118. Okay, B is right. It slows down all the time. That means, or that's because my slope here, big or small slope? Big slope. Big positive slope. Big or small slope? Small. It's negative, right? No, the slope is positive. Big positive velocity, small positive velocity. It's slowing down. It's constantly slowing down. In fact, how would I draw the V versus T graph for this? Well, I start with a big velocity that's positive, and it looks like that. So if I were to draw the V versus T graph for this function, it would look like that. Big positive velocity, big positive velocity. Small positive velocity, small positive velocity. Be able to do that. Be able to take a position versus time graph and draw the velocity versus time graph. I'll be able to take a physical scenario that I described and draw either one of those. I have a couple more for you to practice. There's the slope changing. All right, let's look first at this line labeled A. How does the speed change with time? We're not worrying about this one right now. We're just looking at this. This is the origin for this graph. This is V equals 0. What is what is happening here to the speed? How does the speed change? Remember, speed just considers the magnitude, not the direction, so we're not concerned with signs. Feel free to ask your neighbor what they think. I'm going to stop at 45. 45. All right. V is right. It increases. Nothing fancy here. V is small. Over here it's bigger. It increases. Be able to look at a graph and know what it says. A position or velocity versus time graph. Let's do one more. I think we have time for one more. How does the speed change for line B? For line B. So not worrying about the top line, the bottom line now. What happens to the speed with time? I'm going to stop at 30 seconds. 30. A is not right. The speed doesn't decrease. It does initially decrease, but E is right. Good job, you 8. Let me show you. Let's say this is 5 meters per second. 5 meters per second. 4, 3, 2, 1, 0. 1, 2, 3, 4, 5 meters per second. The speed. Remember, the speed doesn't include the sign. I'm just concerned with the magnitude. This would be like taking something and throwing it up in the air, and it returns back to you. That is this function. All right, looks like we're out of time. We'll finish up these last couple questions, but I'm going to go ahead and post them to the website so that you can print this out and study it over the weekend. Okay? Have a great day. Please prepare for the test. This will probably be our easiest test, so everybody needs to make 100% on it. Bye now.